Namaskar. A very good afternoon to all of you. Today we assembled here to celebrate the important World Earth Day. Actually, the Gerald Nelson was a person who proposed to have a global observance day after one of the most and worst ecological disasters in US. So this day draws an attention to the serious issues like global warming, climate change, and the depletion of natural resources, etc. So to understand the severity in these issues, we have with us today a very eminent personality, Dr. T. Srinivas Kumar Garu, Director, Infois, Hyderabad. So we warmly welcome you, sir, to NGRI. And it is our pleasure to have you on the dais. And I request our director to accompany Dr. Srinivas Garu. I now request Ms. Samina to present a bouquet to Srinivas Garu. I request Simhadri Naidu to present a bouquet to our director. So I request now our director to propose his opening remarks.
Dr. Srinivas Garu, Director Inquiries and today's chief guest. Padma Shri Professor Harsh K. Gupta ji, Dr. B.M. Tiwari ji, former Director NGRI, Chadda Saab, Pishi Garu, former Director NSS, Mangli Saab, my students, friends, and dignitaries online, and ladies and gentlemen. Good afternoon to all of you. I welcome and compliment to all on this 53rd Earth Day celebration. Because due to some unavoidable circumstances, we could not celebrate on 22nd of April. But in fact, most of us know that the Earth Day is the celebration to spread the awareness about the wonder and the beauty of our planet, and as well as the urgency of protecting it. We should remember that each of us is the guardian of this planet, and it is our responsibility to protect it for the future generation. As we all know that 1969, a UNESCO conference in San Francisco, a peace activist, John McConnell, proposed a day to honor Earth and the concept of peace. First observed in 21st March in 1970. Soon after that, United States Senator Gaylord Nelson proposed the idea to hold the nationwide environmental teach-in on April 2022 in 1970. Then he hired a activist, Dennis Hayes, to be the national coordinator, and then after that, Nelson and Hayes renamed the event as Earth Day. Anyway, this is the small brief history of the Earth Day, but it is needless to say that Earth is our home and the source of our life. We breathe its air, drink its water, and eat its food. Our existence depends upon it, and also it is our duty to protect it, therefore. But unfortunately, in the recent time, we face very unprecedented challenges to our planet. We are at the critical juncture to face the challenges of 1.5 degree Celsius increase in the surface temperature of the Earth before 2030, which is not very far from now. Therefore, it is the time to live sustainably, consume responsibly. It is important to check or reduce the carbon footprints of our environment, and also the conserve energy and protect our biodiversity. We need to support the clean technology, encourage the renewable energy, and also encourage the eco-friendly practices. However, in order to invest on eco-friendly practices, we need to explore hydrocarbon, minerals, and also the water. Therefore, our R&D in such cases, for NGRI, the responsibility is manifold, and we should encourage our exploration strategy also in a sustainable way. The water, we have to also advise the mining in a sustainable way. We also advise the extraction of water in a sustainable way. We continue, but we know that development of any country is dependent upon the resource, and we have to explore the resources continuously. And also we know that less than 10% of the Indian territory has been explored till now using the modern tools. And also that is the surface and just below the surface. And also if you see the carbon emission by different countries, the topmost is China. Its world share is around 29.18%. US is around 14.02%, and India is only 7.02%. Our share is therefore very, very low compared to other countries. But in spite of that, we have to reduce the greenhouse gases and also reach net zero emission. Therefore, this year, 2023 World Day, the theme is invest in our planet, calling for the businesses to shift towards sustainable practices. Yes, it is a continuation of the successful 2022 campaign. The movement is expected to change the climate business climate, political climate, and also to take action on the climate. But the responsibility of the NGRI, expectations, and also the expectations. With the core competence spanning for last 60 years in different disciplines of our sciences, we have developed the expertise in earth sciences. CSIR-NGRI is now capable of delivering any scientific solutions to such type of problem to a great extent. For safe planet, sustainable development is must. And therefore, CSIR-NGRI, I found, fits at least 4 to 5 agenda of out of 17 SDGs. And now we have the capability in designing a safe and economic carbon storage system aligning with the mandate to net zero emission of the world. Over the next few years, the Institute shall primarily engage in resolving some of the fundamental issues of science, translating its knowledge for the generation of the generation of the economics, contributing to the economics of the country. And CSR will continue, NGRI will continuously strive for the regional development and prosperity. With this, I will stop here now. And once again, I will compliment you and thank you very much for coming here. And also I thank our Dr. Srinivas Garu for accepting our invitation and coming over here in a very short span of time, and express my gratitude to him for accepting our invitation. Thank you very much.
Thank you, sir. Though we know that the introduction is not required for Dr. Srinivas Garu, but I would call upon Dr. Payal to introduce our chief guest today.
Good afternoon, everyone. So it's my pleasure to introduce our distinguished speaker today, Dr. T. Srinivas Kumar. So Dr. Kumar is presently the Director of Indian National Center for Ocean Information Services in COIS of the Ministry of Earth Sciences, Government of India. He has more than 25 years of research experience. He has worked at various positions and managed large scientific projects at various capacity and roles at several prestigious organizations. So before joining INCOIS as a director in August 2020, Dr. Kumar was heading IOC UNESCO's Intergovernmental Coordination Group, Indian Ocean Tsunami Warning and Mitigation System in Australia. And during his tenure there, he was instrumental in strengthening the regional tsunami early warning systems in active collaboration with 28 member states, global harmonization of tsunami watch operations, and implementation of the Tsunami Ready Community Recognition Program. Prior to that, he was also the head of the Advisory Services and Satellite Oceanography Group at INCOIS, and his contribution during that period led to the successful implementation of various important projects that are related to tsunami early warning system, potential fishing zone, advisories, multi-hazard vulnerability mapping, coral reef bleaching alert system, and many other areas. These projects provided valuable and impactful services to the coastal community of India. And after the 2004 Indian Ocean tsunami, he played a pivotal role in establishment of the Indian National Early Warning Center for Tsunamis and Storm Surges at INCOIS. Dr. Kumar was also elected as the Vice Chair of the IOC 2021-23 during 31st Assembly of Intergovernmental Oceanographic Commission of UNESCO. And Dr. Kumar is a recipient of various national and international awards, including the prestigious National Geoscience Award 2010, towards his contribution in establishing world-class tsunami early warning center at INCOIS. And he was also a recipient of Indian National Geospatial Award in 2008, instituted by Society of Remote Sensing for his contribution towards application of geospatial technology in disaster management. So Dr. Kumar holds a PhD in Oceanography, Marine Sciences, and has more than 70 research publications to his credit, and has contributed chapters in 5 books. So with this brief introduction, we welcome you here, sir, and I invite you to deliver your lecture. We are very much looking forward to hearing you. Thank you.
Very much, Dr. Payal, for the very generous introduction. Dr. Prakash Kumar, Director in GRI, Dr. Harsh Gupta, my mentor, I would say, former Secretary, Minister of Earth Sciences, and Dr. Chadda, Dr. Tiwari, Dr. P.C. Rao. I mean, I've known several colleagues from NGRI, all the students sitting out there, all the senior colleagues from NGRI. First of all, let me thank you for inviting me to be here at NGRI and then be part of these Earth Day celebrations. So I again would like to congratulate all of you on the kind of work that you do in earth sciences. And then I will try to actually give a bit of glimpses of what we do as an organization at INCOIS in the ocean space, especially, which is a big component of the entire Earth system that we are all talking about, and then we all work on. So if we talk about the Earth system, some of these a couple of slides here would be just introductory, just to set the stage for what I'm going to talk in the next half hour. So we talk about the atmosphere, we talk about the lithosphere, cryosphere, and the ocean. Then the biosphere, which actually exists, cuts across all these spheres that you see there, and the interplay of each of these actually, and then the interaction and feedback. They determine our climate, our weather, and our entire existence on the planet Earth. Director NGRI was talking about it in his opening remarks, actually. So if you come specifically to the oceans, there are 70% of the Earth system is covered by the ocean. And there are several modes of variability that we need to understand. In fact, oceans, even about a decade back, 10 to 15 years back, they were considered to be very passive contributions to the whole Earth system. Only about 15 years back, that is, when the Ministry of Earth Sciences was established, that was the time when there was a lot of importance, even globally, a lot of people understanding that oceans are much more than passive contributors to the whole Earth system, to our weather and climate. So 70% of that. So we need to understand all of those things actually to be able to understand how the oceans contribute to the Earth system. I've mentioned this, 70% is oceans, and then the entire climate, our climate is regulated by the oceans because the oceans transport heat from the equators to the poles and vice versa. And then they also regulate our weather. The monsoon, we talk about the monsoon. We now know that oceans play a key role in actually how the monsoons, perform. And then, of course, the air we breathe, 50% of it, every second breath we take, it comes from the oceans. The ocean phytoplankton, it actually takes up the carbon dioxide that is generated out of natural and the anthropogenic causes, and then they release oxygen, and 50% of the entire planet's oxygen comes from the oceans. And of course, they have a lot of uses, the oceans. We use them for recreation, we use them for transportation, food, a lot of food, source of protein, it comes from the ocean through the fishes that we harvest, the marine fisheries. Of course, there are drugs from the oceans, which are very important. And of course, they have a very strategic role. 50% of the human population and 70% of the megacities, they are located near the coast. 90% of the global fisheries and 25% of the global biological productivity through the phytoplankton, both micro and macroalgae, it comes from the oceans. And again, world's energy supplies, both renewable and non-renewable. Tidal, you talk about tidal, thermal, gas hydrates, of which a lot of work was done at this very institute. All of them, about 25 to 30% of the world's energy comes from the oceans. And of course, very important thing is the disasters. I spoke about monsoons. Over and above that, the disasters like the cyclones, the storm surges, and the deadly tsunamis, they all, they are bred by the ocean. So we need to, coming to the Indian Ocean again, the Indian Oceans are very important. Indian Oceans being very small as compared to the Pacific and the Atlantic, but the kind of importance that they have in the total ocean and the Earth system is huge. And there are several reasons for that. For example, the other oceans are ventilated, both from the north and the south, whereas the Indian Ocean is not ventilated to the north. So it actually plays a huge role in the transport of mass and heat. So the Indian Ocean is very important again, because if you see the entire Indian Ocean rim countries, 28 Indian Ocean rim countries, most of them are developing economies. And then we have started to give a lot of importance to the blue economy in each of our countries. In fact, India is also coming up with its own blue economy policy on how we need to actually harvest the oceans, but do it in a very sustainable way. That's what we call blue economy. So most of the countries in the region, they are developing countries who are working on their blue economies. Then we are mostly agrarian societies. We depend on agriculture, which means we are dependent on the monsoons, which are impacted by the oceans. Then fisheries, of course, about 4 million metric tons every year is the fish harvest, marine fish harvest from of India, from the Indian coastal areas. We don't do a lot of open ocean fishing into the EEZs, but then our coastal fishing, it contributes to 4 million metric tons, about 600,000 families of fishers, they are dependent on the fishing. And then our coastal populations are very vulnerable to extreme weather events and also climate change. Now, there are a lot of science drivers, all of you colleagues here being scientists working on earth science. Also a lot of ocean, science problems that we as oceanographic community try to understand. For example, we talk about oxygen minimum zones in the oceans. We know that the Arabian Sea has huge oxygen minimum zones. And then we have actually identified them several years back, but we know now that the extent of the oxygen minimum zones is expanding. So that's something we need to be worried about. There are also then upwelling and subduction zones, like for example, the the southwest coast of India, which is Kerala, during the monsoons, it actually brings along a lot of nutrient-rich cold waters from bottom to the surface. It's called upwelling, and upwelling leads to huge productivity, which leads to, again, the primary productivity, secondary productivity, and tertiary productivity. So the upwelling is a huge thing that we need to understand a lot more. And we also need to understand the major heat fluxes and sea level rise, how the heat is getting accumulated in the oceans, and then how it is impacting, the melting of ice caps or thermal expansion of the seawater, which is again leading to a sea level rise and then inundation of the coastal areas. Then we have the tropical modes called the Madden-Julian oscillations, which are an atmospheric phenomena, which also impact the oceans. When we talk about modes called Indian Ocean Dipole, I'm sure a lot of you have heard and worked on ENSO, which is called El Nino Southern Oscillation, which is actually a phenomenon in the Pacific, but then impacts the global climate. We have a similar mode in the Indian Ocean called the Indian Ocean Dipole. So all of these things are some things we need to understand. So Indian Ocean is a kind of I would say, a test bed for research in terms of oceanography. So not only India, a lot of countries in the Indian Ocean, as well as the global scientists are working in the Indian Ocean to understand all these aspects. And then, of course, we also need to understand, we have operational drivers in addition to the research drivers, because we need to actually, for example, we need to observe the oceans, we need to understand the oceans, we need to model the oceans and predict the ocean. For that, there are certain operational drivers. How do you improve the surface fluxes that you actually use in your ocean models? How do you assimilate data from your observational systems into the ocean models that can give you some meaningful predictions to be able to generate operational services or to develop policy? And of course, we need to be able to do seasonal to subseasonal forecasting. So just, a summary to say that oceans are very important. And then when we talk about oceans, what is that? How do we understand the oceans? So we need to, the oceans are measured in terms of certain parameters, the ocean health. These are called the essential ocean variables. So you have essential variables of the Earth system for ocean and climate. Of course, what I've listed there, they are the ocean variables. So if you are able to measure and then monitor those variables, we'll be able to get the pulse of how the ocean is functioning as an ecosystem. So those span about, there are about 30 variables currently. There are about 2 more variables that are being added. So this is something the scientific community sits together. This has been decided by the GOOS. It's called the Global Ocean Observing System, a group of scientists working under the Intergovernmental Oceanographic Commission and the World Meteorological Organization and so on, which actually decides these are the key variables. Of course, there are several others, but then these are the minimal set of variables that need to be measured. So they span both physics, biogeochemistry, biology, ecosystems, and several of them are also cross-disciplinary. Like, for example, you see sea surface temperature, then temperature at a certain depth, and you have chlorophyll, which is a biological variable, then you have nutrients, and you have mangroves, for example, say the ecosystems, coastal ecosystems, grasses, and so on and so forth. So these measurements help us identify the connections between the ocean and the Earth system. So that's why we need to measure all those variables. And then there are also a subset of variables which are coming from ocean, land, as well as atmosphere, which we need to measure together and then understand the relations to understand our climate. So those are called the essential climate variables. So I don't expect you to go through each of them, but I'm trying to explain why observations and services, that's where my talk is going to concentrate on. So I'm trying to put the background out before you, why oceans are important, what we need to observe in the oceans, and then I'll come to a bit about how we observe the oceans and what kind of information that we generate. So the oceans, unlike the land-based observations, which most of you do, land-based observations themselves are very tough. It's very difficult to put instruments where we want them and observe what we want to observe for all our projects. But ocean observations is a bit more complicated than land-based observations, just because of the fact that oceans are very inaccessible. You need to actually really take a ship and then go and make measurements. That was how the traditional ocean observations were made. But then now, for the past decade or so, there are a lot of other advancements that have happened to actually observe the ocean. So the point I'm trying to make here is, what are the you need to observe, then what you can do with the data, and then how do you actually develop, for example, a service operationally or a policy. That's called the ocean value chain. Starting right from observations on the top, then you actually, those observations could be measured through satellite or in situ data. Then you actually get the data, manage the data. Either you have archives or you have real-time data systems that can provide data for data assimilation. Then you have modeling. That is where you actually use some of these data sets into numerical models. I'm sure a lot of you work on Earth system models. So we work on ocean models and coupled ocean atmosphere models. And those models are what actually can generate forecasts. Now, those forecasts can lead to several applications spanning climate, weather, and ocean forecasting. Then they could span, ecosystem kind of services like harmful algal blooms, fisheries. Then you could actually get information on severe storm warnings or coastal flood warnings or tsunami warnings, and disaster risk assessments, environmental risk assessment. These are all policy-related kind of products. This is actually something that we call the entire ocean value chain. Now, this is actually a strategy that comes out of the global ocean observing systems. Like you have scientific communities that you work globally on, solid Earth. The IOC, the Intergovernmental Oceanographic Commission, actually puts together scientists within the ocean domain to come up with a strategy, because this is not something what happens in someone else's backyard in the ocean can impact what happens in the Indian coastal areas. And then there is no single country that can go out and do observations on its own. So that's why there is actually a strategy, which is a joint strategy subscribed and prescribed by all the countries which are involved in the GOOSE program, and then trying to make observations, make sense out of observations, and then derive products out of observation. So now that's on the broad, global kind of framework. Now, what happens? What do we do in India, in INCOIS? Now, within India, again, there is a very strong institutional mechanism, thanks to pioneers like Dr. Gupta, who was the Secretary of the Department of Ocean Development, sir. You remember those days, how you advocated, that we should have a ministry that deals with earth sciences. And then thankfully we have that. And India would be only, I would say, 2 or 3 countries which handles earth system as a whole. US has something called NOAA, for example, the Ocean and Atmospheric Administration. So similarly, there are not many countries. A lot of countries do oceans independently, fisheries independently, atmospheric sciences independently. Of course, even in India, we have several institutes that deal with all these aspects of earth system sciences. But then there is a responsible ministry that deals with, some of these aspects of oceans, atmosphere, etc., all together in different institutions, and comes up with science, and then science that actually again leads to policy. Those are all the institutions that are listed there, which are under the Ministry of Earth Sciences. But then there are, like I mentioned, other institutes, very important institutes like CSIR-NGRI, whom actually a lot of collaborative work happens between, within the MOS institutes, even within COIS. The CSIR-National Institute of Oceanography, which works on ocean sciences. And there are institutes outside, like, for example, the Geological Survey of India, which actually survey the marine coastal areas. So these are all the institutes that are involved in the earth sciences. Now, coming to INCOIS, specifically under these institutes, INCOIS deals with ocean observations and ocean information services. How is National Institute of Oceanography, Goa, under CSIR? What does it do that is different to INCOIS? NIO does a lot of work on ocean science, the basic understanding of the science. INCOIS works on applied science, applied research, and then trying to see how the knowledge generated within the country in various institutions or globally can be converted into a service that actually has some societal application. In simple terms, if I can say, like, for example, the meteorological department, you see, it generates, forecasts on weather or cyclones. Similar information for the ocean is generated by INCOIS. So that's the kind of role that we play in this entire ecosystem. So our communities, the user communities that you see there, Those are the communities that we serve, starting right from fishing community to coastal states with Met departments, strategic users like the Navy, hydrographic officers, Coast Guards, ports and harbors, shipping. So anybody who has, anything to do with the coastal or open ocean. So we actually have something, that can benefit them, either their operations, their lives, livelihoods. So what are the kind of services that we generate for them? Like, for example, we can categorize them under different services. The ecosystem related services, which I mentioned before, then ocean state forecast services, disaster related services like tsunami early warning and so on, coastal geospatial services, then data related services. We have weather and climate related services and capacity building. Now, how do we generate these services? I'll get into a bit about each of those services in the time that I have left. So I'll not get into that part now. But generating the services, like I mentioned before, needs observation. Now, those could be remote sensing, in situ, and then we need to actually synthesize those observations, run models, and then we have a lot of other scientific programs called satellite oceanography, which we use to actually derive geophysical products from raw satellite data. Then we have ocean science and modeling, which we actually, where we try to work with several organizations to develop and build models, numerical models. And then actually also we have high performance computing facilities available within the country, within the ministry, which we use to actually generate some of those products. So coming to the observations, Indian Ocean a decade ago was the least observed ocean. So if you need to go and observe, you need to take a ship, go there. If you cast one CTD profile, there would be 10 scientists looking at one single CTD profile or a few CTD profiles and trying to understand what is the temperature structure within the ocean or salinity structure or how the circulation is moving, how is the coastal circulation along the Indian coast and so on and so forth. From there, now today, we've actually come to a stage where we are data rich. I wouldn't say that we have all the data that we need for all the parameters, but we have certainly improved, in the past couple of decades. So we compete with any other ocean, in terms of observations. So that's the map that you're seeing there on the right. So those each and every dot there is an observational platform, more or less in real time. So those green dots are, for example, called Argo floats. So these are the kind of floats that you have here. These are the Argo floats. Sir, you remember in 2001, we had this Argo International meeting, which was held in Hyderabad. And that was the starting point for this Argo program within the country, within the Indian Ocean region. And India was the first country that went ahead and said that, okay, we'll deploy Argo floats and we'll be responsible for the Indian Ocean region. We still continue to play that role, sir. So we have a lot of Argo floats that we deploy. So similarly, we have ECFS measurements. Those are flux measurements that we make, flux moorings. Then we have new observation platforms called gliders. I'll talk about a few important, observing systems that I think might interest you for your research, and then you might be interested in those data sets. So we run automatic weather stations on ships, high frequency radars, which can give coastal currents in all the coastal areas. Then we have tsunami buoys, we have tide gauges, then we have mood buoys. So that's the kind of, at any day, if you look at, what are all the observing systems that we receive data from, that would look like something, like the map on the. In addition, we also have several remote sensing satellites. Remote sensing satellites, I would just mention, there are a lot of satellites, both Indian and foreign satellites, which actually work across the electromagnetic spectrum, starting right from visible to thermal infrared, radiometers, going out to, the microwave sensors, synthetic aperture radars, spectrometers, altimeters, which can give a host of parameters starting right from sea surface temperature to ocean surface winds, to ocean surface salinity, and ocean waves, ocean surface topography, which is the height. So all of those things. So one satellite, India has a very strong ocean satellite remote sensing program, thanks to ISRO, and then the collaboration that they have with the Ministry of Earth Sciences. Very recently, in October last year, 2022, India has launched an ocean sat, That's the third in the series of OceanSat satellites. The first satellite was launched in 1999. Next one was in 2009, and very recently the third one. It's a very important satellite. If somebody is interested in looking at the data, INCOIS receives the data. So it's still being operationalized. In orbit testing is going on of the sensors. So there are two very important sensors. One is the ocean color radiometer, which has actually about 13 bands, which can give you information on sea surface chlorophyll, total suspended matter, water clarity, which is actually K490. It's called diffuse attenuation coefficient. All those. So it's a 13-band radiometer. And other important sensor is called the sea surface, spectrometer. And then there's also a sensor for sea surface temperature monitor for sea surface temperature measurements. So there is a big, satellite program that we actually depend on for, making observations of the ocean. This is the Argo float. Without getting into too much of detail, why Argo floats are important. Argo floats can measure temperature and salinity. They can go up to depths of about 2 kilometers. Once you deploy it from a ship, it can go down, or it can be deployed from an aircraft. Very inaccessible seas, you can just drop the float. It can go down and measure. While coming up, it measures temperature and salinity, transmits the data to a satellite, goes down again. It can make about 125 cycles. Each cycle can be 10 days. Now there's a lot of development in the Argo technology itself. Previously, it used to be one-way communication. The float could only communicate to us. Now there is two-way communication. We can communicate to the float, then ask the float to make either more frequent measurements or more measurements only in the upper, say 500 meters. If there is a cyclone, I want to make more measurements of the surface. That actually could be programmed. We could send that commands onto the float, and then that float could make those measurements. Why temperature and salinity are important? Because they actually can give an idea of the heat and mass transport. So that data directly gets into ocean models actually. So this is a global program, about 3,000 Argo floats all along the globe, all those dots that you're seeing there. And INCOIS is responsible for Argo float program in the Indian Ocean. We deploy about 50 floats every year. That's the kind of investment India puts into the Argo float program. All the data is shared internationally with all the forecasting centers, as we also receive data from all the 3,000 floats at INCOIS. So it's fully shared. Now, flux mooring, again, very important. Force or ocean models, we need fluxes, radiation fluxes, wind fluxes. So all this is the first time that such a flux mooring has been deployed in the Indian Ocean region. This has been done by INCOIS in collaboration with the Woodsole Oceanographic Institute. It actually it is heavily instrumented flux mooring, both on the surface and then below the water. You can measure temperature at different depths, currents at different depths, and all this information again goes into understanding the fluxes. So that's why it's called a flux mooring. Now we are going to redeploy this, take it into the Arabian Sea. Use a lot of information on improving our monsoon, kind of understanding our monsoon and enhancing its predictions. You can measure freshwater fluxes from the Bay of Bengal coming into down south into the bay. So all those measurements can be done using flux moorings. Now this is something which is called a glider, very state-of-the-art equipment. This is called a sloka. Glider. But these gliders actually have about 9 months. And actually program where this glider has to go and what measurement to make. Two gliders. Then we are going to have about 2 gliders. This is the glider that was actually inspected very recently. There are 2 transects of gliders as part of our deep ocean mission. Going up to 5 degrees south. The climate is not warming. It actually changing the cross equatorial currents. So all those things can be measured using these gliders. So this is a very new observation that we have actually started implementing. And this data could be available in real time. And then you could put a lot of sensors on this, not just the temperature and salinity. You can put a chlorophyll A sensor. You could measure color dissolved organic matter or fluorescence. Then you could actually get backscattering, which means you can get an indication of the surface sediments. You can get dissolved oxygen, very important, like I mentioned about the oxygen minimum zones. You could actually send these gliders, ask them to measure oxygen concentrations at various depths, and then send the data back to us in real time. You can measure photosynthetic available radiation. It's a light sensor. It can give you an indication of how much of productivity is possible and up to what depth. All these things. So the gliders are very versatile. You can put acoustic sensors. You can use it for strategic application. Recently, one glider was launched in Perth, Australia, Fremantle, and then it was recovered in Colombo over a period of 6 months. So you can just, it's very versatile. You can make any measurement that you have. Then, of course, being in NGRI, I'm sure all of you would be interested in tsunamis. So we also maintain tsunami buoy systems, about 7 of them, 5 in the Arabian Sea, 5 in the Bay of Bengal, and 2 in the Arabian Sea. And then these actually measure pressure at the ocean bottom that is exerted by the overlying water column. And then that information can be actually sent to INCOIS. If there is a change in sea level, that information, with that, we know that, okay, the tsunami has been triggered and on the way. Of course, it can be used for several other science applications because it gives a very clean signal of sea level in the open ocean, unlike sea level that you measure in the coastal areas. Now, that sea level was used by one of our PhD scholars who actually have, get some idea on the, the barotropic waves, how they propagate from the Pacific into the Indian Ocean. So several such applications also are there for the tsunami buoy data, if somebody is interested. We also have tide gauges. These tide gauges measure sea level at the coastal area. We have about 36 of them. All this data is available in real time. They are used at INCOIS for detecting tsunami waves. This is actually a tsunami. It was in 2012, and it actually triggered a small tsunami near Campbell Bay, which was recorded by these tide gauges. So this is available. This data is available. And something also that might interest you, we also run a network of GNSS stations and strong motion accelerometer stations in the Andaman and Nicobar Islands. Each of these triangle that you see here is a station. Of course, we have received a lot of help from NGRI in establishing that network, and we maintain that network. All this is, the intention is to use it for tsunami warning. I'll talk about that in about, when I come to the end of my presentation, why these things are important for the future of tsunami warning applications that we want to do. So we have about 35 of those stations. So those are glimpses of a few observing stations I thought might interest you. There are several other observing platforms that we run, like HF radars, mood buoys, and so on. If somebody is interested in data or working together with our scientists, we'll be very happy. All the data gets into model and prediction systems. Again, this is something that happened in the last 10 to 15 years, I would say, because before that, it was mostly statistical kind of forecasting, but then the dynamical forecasting using ocean models. So we use a host of models, starting from global models to regional models, and then take it down to very coastal models and estuarine models. We run physical models which can actually simulate ocean physics, biology to biogeochemistry, and we run them at various resolutions, and that is what actually enables some of the products that I mentioned before. So, for example, this is actually a model that called ADSER, and we also have a model which we actually use for tsunamis. So all of those waves, for example, we have models. So there is a very strong ocean modeling program that help us, generate some of the products. I'll quickly come to some of the products themselves. What I said we actually produce. Now, these are the ecosystem services. Just one slide. For example, using satellite temperature and chlorophyll and a lot of other information from models like mixed layer depth, we can tell fishermen where they can go and do fishing so that their catches would be better. We are trying to understand the habitat suitability for different fishes. For example, a sardine likes a certain habitat, tuna likes another habitat actually. So that habitat, once it is characterized through several experiments, then we actually find a way to get those parameters like sea surface temperature, chlorophyll. Like tuna likes oxygen because its metabolic rate is very high, it swims very fast. So if we have a way to identify in real time the oxygen concentration, either through Argo floats or either through gliders, you will have a means to tell whether that habitat is suitable for tuna to aggregate, and then direct fishermen to go and conduct fishing operation. That's something that we provide on a daily basis. And similarly, we also provide a service for monitoring the coral reefs. Coral bleaching can happen when the temperatures are very high. So coral bleaching alerts we give. And like we have heat waves on the land, we also have marine heat waves. We can actually monitor those marine heat waves using sea surface temperature data. Then we have algal blooms, like we have eutrophication that you see in the lakes. Then we also have such eutrophication in the coastal areas due to a lot of nutrient influx. So that is something we actually also have as a service called algal bloom information service, water quality services, and so on. On the marine safety, we have products that actually wave forecast products. Then we have oil spill alerts. If there is an oil spill, we can forecast the trajectory. We have models that can do that. And then we can also provide information on search and rescue. Like, for example, an object is lost in sea. How can you actually, where is the probability of finding that object? Because of winds and surface winds and currents, it gets drifted. We can actually run those models and tell that this is a possibility of finding. So those are some of the ocean forecast products that we provide, not only for India, but for several Indian Ocean rim countries. And we also have wave models that can tell you actually, okay, if there is a cyclone and what is the associated marine. This was supposed to be another animation, but I leave it there. So what is the waves that are associated? Like, for example, these waves are about 6 to 8 meter waves that are actually following the cyclone and then causing inundations in the coastal areas. In fact, this is for Taukte, which killed about 80 people on a barge in the west coast. So those predictions were made almost 5 to 8 days in advance. And then these are the kind of wave buoys that actually measure those waves. And then what you've seen plotted here is the forecast that is actually overlaid with the observations. The red is the observations. And that happens in real time on our website. So people know, or the users know, how good or bad the forecast is doing actually. So, and we also provide information on storm surges. So the IMD gives a cyclone track. We use that cyclone track to produce information on storm surges. What will be the height of the surge and how much of area it would inundate. So those are for the forecasting. Now, coming to a bit about ocean climate services, like I mentioned about Indian Ocean dipole, there are several indicators that we can monitor and say that, okay, now this is going to be a dipole here and so on. So that is something that we actually do. And then we are also having a project that India is actually taken up called the Deep Ocean Mission, sir. So that is something where we are going to actually work on projections of sea level, cyclones, storm surges, waves, and ecosystem, marine coastal ecosystem. How it's going to behave in a climate change scenario, in a higher temperature scenario. So, and what impact that will have on the coastal areas. So that is actually the Deep Ocean Mission. And this Dr. Prakash Kumar mentioned that this 1.5 to 2 degree will be exceeded. This is as per the recent IPCC AR6 report, and that is going to cause sea level changes. Those sea level changes are not going to be common across the globe. They are going to be different. So what is the impact of that sea level rise on the Indian coastal areas? Now that is something that this particular Ocean Climate Change Advisory Services that INCOIS is responsible is going to do under the Deep Ocean Mission. Multi-hazard, again, we have a tsunami warning system, which actually is established after the 2004 tsunami. It was Professor Gupta at that time who actually said that the tsunamis for Indian Ocean can happen only along two subduction zones, which is the Tunda subduction zone here and the Makran subduction zone. Now the entire regional system is built on that premise. All the observing systems, being seismometers, strong motion sensors, or sea level gauges, are all built to actually detect tsunamis from those two subduction zones. So that is something which actually is operational now. INCOIS acts as one of these regional tsunami service providers. This is actually just an earthquake that happened this morning at 1:30 a.m. our time, when all of us were sleeping. Our center detected this earthquake. It was actually finally a 6.8 magnitude earthquake in Indonesia. We detected it within 5 minutes, almost near real time. We produced bulletins, and then we found that from our model simulations, there was not going to be any threat to India or to the entire Indian Ocean rim countries. We disseminated that within 10 minutes. That information was available to the world. And we also monitored the tide gauges. We found that there was a very small tsunami near Indonesia, near the earthquake location. It was only about 11 centimeters, which was not significant. But if it was the largest earthquake, it would have actually, in fact, triggered a big tsunami. But what I'm saying is we are able to monitor those events and give information. So I'll skip a few slides here and take you straight away to, what are the benefits. Most of these services, they have huge benefits. Sometimes we may not charge the users, and the benefits might not be tangible, but then most of these benefits are, economic benefits are, accruing to the users, or they lead to enhancement of safety, or operations. So a lot of work has been done to quantify those benefits. Like, for example, a fisherman can save about 30 to 70% in search time, which means he spends less time on the sea. He spends less diesel, and he also puts less carbon into the environment. So there are economic benefits, there are environmental benefits. Similarly, if there is a tsunami like the one that happened this morning, a large earthquake, and if we have told that there is no tsunami, that means you have avoided unnecessary evacuation of the coastal areas. And this is actually an estimate for relocating and evacuating coastal population during Phylin. What the states have spent, they have spent about 3,400 crores for one event. So just by saying that a tsunami is not going to come, is a big saying. Of course, if you're saying that a tsunami is coming, say lives are saved, which are again invaluable. So just to say that the kind of investments that we make into these things, ocean observation or any science that we all do, I mean, the benefits are huge. So sometimes it actually takes a bit of an effort to explain to the policymakers that we are spending X, but then the benefit is 10X. But these are the kind of benefits that we have. Now, I'm coming to last. I'll take just a couple of minutes. In the global scheme of things, where is the world moving in terms of oceans and the kind of topics that I mentioned? So there is something called UN Decade of Ocean Science for Sustainable Development, which is right now starting from 2021 to 2030. Because, like Director mentioned in his opening remarks, now the world has really, now is the time. I mean, if we miss the bus now, I think there is no, looking back now. So that's the kind of, our Earth has reached such fragile state, and then especially the oceans. So that recognition has come, and the entire UN, under the UN, all the stakeholders have come together to identify 2130 as UN Decade of Ocean Science for Sustainable Development. We must do whatever is possible within our remit to ensure that the oceans are actually sustainable. The resources that we actually use from the oceans are done in a sustainable way. We don't pollute the ocean. We monitor the ocean. We model the ocean. We predict the ocean. We manage the ocean. So that actually is something. So there are several outcomes at the end of the decade, 2030. We want a clean ocean, healthy ocean, productive, predicted, safe ocean, for example, from hazards, accessible, inspiring, and engaging ocean. That means you should be able to involve the civil society into the discussion on ocean. Anybody who is actually in Hyderabad, why does he care about ocean? He's not in a coastal area. We need to bring that connect with the civil society, saying that ocean is important for everybody, and then we need to protect it. And these are the challenges that the Ocean Decade has to wants to address as a community globally. Pollutants, ecosystems. So you talk about anything about the ocean, it is there. Why I'm actually putting this slide in this August gathering is what we want to do as far as safe ocean. So there is something called Ocean Decade Tsunami Program. Now, under the Ocean Decade, several programs, projects, and initiatives are being spun up. Then one such thing, important thing that the global community has come together to improve tsunami warnings is actually called the Ocean Decade Tsunami Program. So what we do under the Ocean Decade has to be transformative. It is not business as usual. And then it needs to lead you to something at the end of 10 years. So that is what we want to do as part of the Ocean Decade. Of course, there are 40 programs, close to 200 projects that have been spun up now with global community addressing several of these challenges. What we want to do in tsunami, I wanted to put forth before you. So there has been progress since 2004, but there are several challenges. So we know that tsunami warning is race against time. There are gaps in warning response capabilities, especially for non-seismic and near-field sources. There are gaps in SOPs and early warning chains, and the gaps in preparedness and response. What we do well is actually for these seismic earthquakes, which are about 80% of the tsunamis are caused due to seismic events. But there are other 20% that are non-seismic. So that is an area we need to improve. What is that we want to know? These are the things like I mentioned. Like, for example, this was the Anak Krakatau volcanic eruption end of 2018, which actually triggered a tsunami. About 400 people died. And none of the warning centers globally could actually do anything about it. Though we had warning systems that were established, I mean, we couldn't produce information that could act as early warning. We monitored the event, fine, but then it was not timely enough to take, action. Similarly, the Palu event, which happened again end of 2018, it killed about 4,000 people. Of course, half of them due to earthquake and liquefaction and so on, but about 2,000 people due to tsunami. And this earthquake, after the earthquake happened, somewhere about 100 kilometers north of Palu Bay, within 2 minutes, the tsunami has actually come to the coastal areas within the Palu Bay. And it was actually, it was found that this might have happened, of course, due to submarine landslides, which acted as local source within the bay and then sent tsunami waves out. So again, none of the centers, they are, equipped to produce a tsunami warning in 2 minutes. It's practically impossible. So you should enhance the upstream capability to actually produce a tsunami warning in time. At the same time, you also need to enhance the capacities of people to respond to natural warnings, say, for example, if something is happening in 2 minutes. So as part of the Ocean Decade Tsunami Program, what is being planned is to reduce the uncertainties in tsunami warning. By 2030, for example, you should have a very uncertain, I would say accurate forecast. You can't have a forecast which is 100%, but then you should be able to bring down the uncertainties considerably and be able to generate a warning within 10 minutes to any part of the global, tsunami-prone regions. So and of course, 100% communities should be prepared and resilient. Now, how that is going to be addressed? There is a science team under the IOC UNESCO. It's been, working together for the past 1 year, trying to come up with solutions that can actually lead us to those lesser uncertainties. So this is actually, the thing is, there will be, the seismic proxies is what we use right now. And from that seismic proxy to develop a tsunami warning, there are certain assumptions, and then there are certain uncertainties. Now, how do we bring down those uncertainties? And then how do we enhance our capability to directly detect the tsunamis? That means build a network of combination of equipment. That means we need to rethink how we do our ocean observations as far as tsunamis are concerned. So it could be, seismic networks enhanced, then tsunameters, or it could be smart cables, undersea telecommunication cables, which could be rigged with seismometers and ocean pressure sensors that could give you a vast, observing capability. So those kind of smart cables could be thought of. And then coastal radars or active remote sensing like altimeters. How can we have several altimeters in orbit, a constellation of them that can detect tsunami waves? Or can you use infrasound observations? Or can you use ionospheric tomography, total electron count based on the GNSS data would be used for tsunami warning? How do you do that? Then fiber optic applications could be used. So all of these things, some are actually things that are existing capabilities, how you can expand them. Some are in the R&D stage, how you can operationalize them, or some are new capabilities where scientific community could come together, develop them. So these are characterized onto all those things. And then, of course, you use techniques like AML, where you have lots of data coming in. How do you use some of these techniques to really put out a warning in time that can make an impact? So this is something that is being planned in the next 10 years. I'm sure all of you, as geoscientists working in earthquake, you would be actually interested in looking at what are some of these problems and then trying to see where you could contribute. So I stopped there. Just before, on an end note, I would also like to bring to your notice that India is working on its own blue economy policy. The Ministry of Earth Sciences is spearheading this initiative. Talks about several priority areas, like, for example, coastal tourism, marine spatial planning, shipping, fishing, and deep sea mining, ocean energy, and security strategic dimensions are there. And of course, the first step is national accounting framework. Right now, we don't know what is in the oceans. How do you account for that, wealth and resource? And that is something also which is one major pillar. So I think all that we do all together as a scientific community working on earth science, both on oceans, solid earth, I think we have a great deal to contribute to the, the blue economy policy, the deep ocean mission of the government of India, and then also like, programs like the UN Ocean Decade of, sustainable development, so making us all stakeholders, keeping our planet sustainable. Thank you very much.
Yeah, with your permission, can we have, if anybody is some query, they can ask, sir. Yeah.
Regarding tropical cyclone, now there are very advanced softwares which we can, like, anybody can able to see where it is moving and how it is landfall, all these things. But the thing is, even though we can able to track it 5 days, 7 days before, we cannot stop it. So basically, it is a low pressure system. If we can have something regarding, like, we can increase the pressure or something like to destabilize the pressure, then something can happen. We can stop it within the ocean. We can stop it. But means it is like compared to the tsunami, it is quite a long process. 7 days, 10 days we have. But then why we cannot able to adopt those type of things?
No, see, these are, we are talking about, huge, these are large systems actually. Theoretically, it looks like, this is something that we can do, but then, weather modification technologies, like, for example, cloud seeding, or, you want to actually change the pattern of rains. These are some things that are actually tried at a, at a very small scale. But then something, the kind of energy that is actually involved in the cyclone system, the kind of, for example, the cyclones are formed on, hot, it's because of this, the heat content in the water. And then that kind of heat content is so huge, actually. There's not anything that practically you can do to really change the course of a cyclone, not at least, at this stage, actually. Weather modification technologies, like I mentioned, for certain things, they're being used, like, for example, cloud seeding, and they talk about, the changing the, patterns of rainfall. But then, the cyclones and tsunamis, all these things are, too huge for those things. What they no, you can't do that actually. So not at that scale. They are too huge actually. It's like, talking, you have a big truck going. I'm giving a crude example, and then it's like an ant, trying to, stop that huge truck actually. That's the kind of scale that we are talking about. It's huge. It's huge. Like, for example, tsunami. It's huge. It's not that even for tsunami there are no engineering solutions. Like, Japan has built a big network of seawall. Okay, so they're actually designed and built there to stop the impact, not fully, but at least reduce the impact of tsunami wave. So there are engineering solutions that can be used for, certain to a certain extent.
Nobody is there. Okay. Sir, it was indeed, it was a very, very detailed and wonderful talk. And we feel energetic after hearing this talk. Otherwise, it is a sunny, hot day. The culprit which reduces our energy levels. So hearing the oceans, waters, and it will lessen the heat. So thank you very much for this. And we could understand the importance of oceans in regulating many other ecosystems of our life by studying the variations in the ocean dynamics. And your talk also throws a light on the global strategies to protect the oceans, which are important for the aquatic life as well. So it is also heartening to know about the significant contributions and progress in different observing systems carried out by the ENCOIs. So these are, I think, praiseworthy contributions, and hearty congratulations for this, sir. And thank you very much. And it's a pleasure moment now. We will felicitate our chief guest today. I request our director to felicitate Dr. Srinivas.
Make a comment before, can I make a comment? You see, listening to him was a pleasure, of course. And there are very few areas where India has stood up and matched and excelled on global. And setting up of tsunami warning system, for which he has been one of the main component in setting it up, is one of them. And I must also give him credit for his individuality. You know, a person holding a P5 post in UNESCO, opting to come back to India is a huge thing, and that deserves to be appreciated. Thank you. It's a pleasure to welcome you. Thank you.
I would call upon Dr. Shiv Ganguly to propose vote of thanks.
Thank you, madam. Good evening, everyone. So first of all, I would like to express our gratitude to our today's guest and speaker, Dr. T. Srinivasa Kumar, for kindly accepting our invitation to give a talk in this very beautiful, important event, that is Earth Day celebration. And regarding that, I think you all will agree with me that he gave a very phenomenal talk, and it is thought-provoking, and you enlightened us with the ocean services and how MOS Inquest is helping to the common people also. And you also helped us to open our mind into the future perspectives into the ocean sciences, what could be done, and how every scientist can contribute to that. So thank you so much, sir. And also we'd like to thank information section, electrical section, and canteen section. I mean, those who are background, they acted as in the back scene that the program should run in a very smooth way. Thank you so much. And finally, I would like to thank everyone who take their time out to come here, because without audience, nothing is possible. So thank you so much for being here. And I hope you all enjoyed this talk. Have a great evening. Thank you.
Thank you, Dr. Ganguly. I now request all of you to join us for high tea in the car parking main building. Thank you so much.